Hello, I am Philip Tanofsky, a graduate student at Citi University of New York School of Professional Studies in the Master's Program for Data Science, and I'm presenting my final research project titled Predicting City Bike Availability in New York City for course DATA698 in the fall semester of 2022. The Citi bike share system provides an option for first and last mile connectivity in the urban area for individuals wanting to access the subway or bus line without walking. Citi Bike offers real-time availability of bicycles through the Citi Bike app, but the availability of a bike at a docking station near one's current location is not guaranteed at any time. The availability of bicycles is dependent on the riders themselves and the rebalancing strategies of the Citi Bike operators. As the pictures indicate, zero availability is a reality, so how to avoid an empty docking station? For this research project, as mentioned, the problem is Citi Bike offers live map of availability for immediate bike rental, but the availability of a bike at a location at a future date and time is not guaranteed. So the objectives of this research project are to construct a model of the bike share system usage and availability patterns across New York City, and second, predict the number of available bikes in Brooklyn within a quarter mile of a given location with user-friendly inputs. A few articles were quite informative to this project, and they include, first, Wang, Lindsay, Schoner, and Harrison applied log linear and negative binomial regression models to evaluate the factors of population size, trip attraction, and transportation network as primary factors on average daily station trips for the bike share system. Wang and Chen explored built environment, bicycle infrastructure, and transit-related factors to predict bike share station capacity using several models, including negative binomial, zero inflated negative binomial with structural equation model, and finally a combined zero inflated negative binomial with structural equation model. Third, Hyland, Hong, Pinto, and Chen use a hybrid approach combining clustering and regression to model the bike share usage. The clustering approach separates stations into clusters based on types of trips and proximity. Then they applied regression algorithms to forecast interactions between the station clusters. And finally, Madar, Deschardins, Caruso, and Thomas focus on existing rebalancing operations through spatial and temporal exploration of bike share trip data across many cities. For data collection, the ride trip data is freely available from the Citi Bike System Data website on a monthly basis. The Citi Bike system offers a live API to also retrieve real-time data. My data collection followed both approaches, in which I downloaded the trip data for August through October of 2022. I also set up a recurring script to call the Station Status API every 15 minutes for 2 weeks to capture the accurate availability count for every docking station for the given 2-week period of Monday, October 31st, 2022 through Sunday, November 13th, 2022. The borough and New York City neighborhood coordinates were retrieved as a GeoJSON file from the New York City Open Data website, and station elevation was retrieved via longitude and latitude lookup with the Elevator R package. Of note regarding data aggregation, with the 3 months of ride trip data, I was able to create a data frame that identified the net difference of bikes per docking station for every 15 minutes across the 3 months. Some high-level statistics of the 2 data collection steps. For the 3 months of ride trips, as mentioned, the data covered 92 days of August through October. The Citi Bike data is the only trips originating in New York City. The New Jersey-based trips are not included in this research. The total number of trips is over 10 million. The number of unique stations included in the data is over 1,700. And interestingly, there are almost 25,000 trips I labeled as abandoned, as the trip data did not include a destination, station, and ID. Note, there is a fine from Citi Bike for not returning the bike to a docking station. The bike availability data spanned the 14 days of October 31st through November 13th. This data included all the system stations, but my focus will be on the borough of Brooklyn. Within Brooklyn, there were 474 unique docking stations considered in the prediction model. Given the count of over 10 million trips and over 17,000 docking stations in New York City, it's quite a large data set, which on one hand makes for what we believe to be some interesting visualizations, but on the flip side pushed our computing powers to its system constraints, and ultimately was the reason for focusing the prediction model on Brooklyn instead of the entirety of New York City. Another challenge was accounting for rebalancing performed by the Citi Bike staff. Rebalancing is the movement of bikes by the system operators, which are not accounted for in the 3 months of bike share data. For each of the 3 months, the bike share staff rebalanced over 78,000 bikes, which equates to an average of over 2,000 rebalanced bikes per day. This inability to comprehensively identify rebalanced bikes was the motivation to call the API for accurate availability information. In the final challenge identified, we wanted to build a model to predict the bike availability and make the model user-friendly. We envisioned a website or app requiring just a few inputs from a user to then provide the model prediction. This constraint forced us to limit the model inputs to information likely available to a given user. Now for some exploratory data analysis. Here we have a plot of the 3 months separated by user type, members and casual. Members pay a monthly or annual subscription, while a casual user pays by the trip. The plot shows an expected repeated weekly trend with higher usage by members on weekdays, while casual users show higher volumes on the weekend. Overall, the member volumes are quite a bit more than casual users. Next, we present the weekly seasonal plot of the 3 months of bike trips. Here, we more clearly see the weekday pattern of members with spikes at morning and evening rush hour times. The casual user shows higher volume on the weekends and a weekday pattern with a spike around the evening rush hour, which may indicate some casual users returning home from work or potentially tourists returning bikes in the early evening before a night out in the city. With a 3-month summary of bike trips for each docking station, the map of New York City indicates whether a docking station had a surplus, which is identified in blue, or more arrivals, a shortage identified in red, or more departures, or actually broke even over the course of the 3 months, which is identified in green. And yes, there are a few green dots in this map. This data aggregation plotted on the map of New York City shows the overall direction and pattern of bike usage. Large red areas of Manhattan indicate rebalancing must be occurring to get bikes back to certain areas of the city, and also indicate rebalancing could be increased to address these red areas of the city. As we see there is a shortage in Midtown, in the Upper West Side, whereas we see surplus in the East Village, Greenwich Village, West Village, and Soho. Also in Brooklyn, we see more bikes arriving on the western side, such as Williamsburg and downtown Brooklyn, along with Park Slope. Now, to take a step deeper, we've taken the average arrivals and departures across all Wednesdays of the 3 months, purposely picking a weekday to see the movement throughout the day. Starting at 5 a.m., mostly green, indicating likely little movement of bikes. At 8 a.m., we see arrivals in Midtown and the Financial District, 2 locations of commercial offices, while we see red in more residential areas of Upper West Side in the East Village. At 11 a.m., primarily green as the morning rush has subsided. 2 p.m., similar to 11 a.m., mostly green. Then at 5 p.m., we see the opposite of the 8 a.m. map. Here we see red, more departures from Midtown and the Financial District, with more arrivals in the Upper West Side and East Village. 8 p.m., similar to the 5 p.m., we anticipate the movement of bikes away from commercial areas toward residential areas, with many green stations throughout the city. Now, to get into the overview of the algorithm. The goal of the algorithm is to predict the number of available bikes in Brooklyn within a quarter mile of a given location. The prediction algorithm was scoped to Brooklyn due to the overwhelming amount of data. The 17,000 docking stations proved too much given our computer processing constraints. The inputs, again user-friendly, are location on a map, day of the week, and time of day. The algorithm is composed of a 2-step modeling process. First, the 474 Brooklyn docking stations are hierarchically clustered based on a distance of 400 meters, roughly a quarter of a mile. Then, with the availability counts from the API summed to the cluster by time interval, we apply several general linear models, or GLMs, using count models as a base, such as Poisson, negative binomial, and zero inflated to predict the number of available bikes. The zero inflated model algorithm, as the count of zero bike availability, is common throughout the docking stations of Brooklyn. The map plot shows the docking stations with frequency of 0 bike availability. Most docking stations have a lower frequency of 50 or less occurrences across the 1,344 15-minute intervals of the 2-week period. We do notice a number of red stations indicating high frequency of 0 available bikes. These stations could be considered for greater rebalancing. This plot supports the need to consider the zero inflated model for our purposes of prediction. This line chart shows the number of available bikes every 15 minutes for docking station 3582 in Crown Heights, Brooklyn. Clearly, four spikes to 20 or more available bikes occurs within the 2-week span. These sudden increases, or examples of rebalancing, are inconsistent and always return to under 10 available bikes. This chart indicates the departure usage is driven by the available bikes, but the arriving bikes remain low during this time span. Given the common yet inconsistent occurrences of rebalancing, we decided to not impute the instances of rebalancing, but instead keep the data as accurate in an attempt at a more valuable model. For the predictors, we finalized the inputs as longitude and latitude, anticipating the end user would actually be providing their GPS coordinates at the time of use. The day of the week is converted to either weekday or weekend in order to simplify the model. The time of day is converted to the start of the hour. Models were constructed using the 15-minute intervals, but the results from the 15-minute intervals showed no improvement compared to the 1-hour intervals. Finally, elevation of the cluster was considered, as anecdotally, stations with higher elevations have fewer return bikes. The elevation predictor resulted in little significance of the model and thus was omitted. As for the model algorithms, as mentioned earlier, we focused on the generalized linear models based on Poisson, quasi-Poisson, negative binomial, and zero inflated. The availability data meets most of the Poisson regression criteria. The response variable is a count per unit. The observations are independent. Unfortunately, the variance is greater than the mean, which indicates we do have overdispersion in the data. Thus, the reason we selected negative binomial and quasi-Poisson as base algorithms in addition to Poisson. Also considered but not used was the time series forecasting model approach. Because the forecasting did not allow for instance predictions and would have relied on a more constant up-to-date info, we decided not to include the forecasting approach in the final report. For the clustering, again, we have focused the prediction model on the borough of Brooklyn, which contains 474 docking stations. Using the hierarchical clustering from the Stats R library with a distance cutoff of 400 meters or a quarter of a mile, we ended up with 213 clusters, or a little over 2 docking stations per cluster. The map plot shows the docking stations colored by cluster number. The histogram shows the frequency of availability counts across all the Brooklyn clusters for each 1-hour interval for the 2-week time span. Here, we see 0 is the most frequent value, followed by 2. Also, we see a plateau starting around 25, which marks the station capacity. We also see a similar plateau around 60, close to double the single station capacity, which would be expected given most clusters are 2 docking stations. The plot confirms the decision to use the zero inflated models. Now, for the heart of the prediction model, we apply 5 distinct models to the availability counts by cluster. First, we use Poisson from the stats library, followed by quasi-Poisson, also from the stats library. Then we attempt negative binomial from the mass library, and finally zero inflated, once with Poisson and once with negative binomial, relying on the PSCL library. We trained on a sample of 75% of the data and tested on the remaining 25% of the data. To evaluate the 5 models, we made the selection based on the root mean square error, RMSE, and mean average error, MAE, along with the counter predictions greater than 0 when the actual value was 0, noted here as missed 0. The zero inflated Poisson-based model performed the best, according to RMSE and MAE, followed by Poisson, quasi-Poisson, and then zero inflated negative binomial-based model, and finally negative binomial itself. Assessing the missed 0 column, we notice Poisson, quasi-Poisson, and negative binomial with the fewest missed zeros at 263, followed by the zero inflated models with 280 missed zeros each. As the earlier plot of bike availability count frequency by clusters showed, 0 was the highest frequency, but did not represent an outlier within the frequency distribution. Perhaps the zero inflated models performed worse at correctly predicting zeros because the 0 frequency wasn't actually inflated as compared to the other values. In the end, we selected the base Poisson model because it resulted in the second best RMSE and MAE and had the fewest missed 0 count. The Poisson regression equation is presented for the selected model. Overall, the 25% test data consisted of over 17,000 rows for prediction. The line plot of the prediction subset does show the similar lines of prediction in blue and actual values in red. We do notice that actual values in red reach the zero axis while the blue line does not as often, again indicating the inability of the model to accurately predict the true zero values. Upon visual inspection, the consistency of the two lines does appear close. Now, with the prediction model selected and complete, we wrote a function to put the model to practical use as a proof of concept to predict the number of available bikes based on the user-friendly inputs. The output of 3 trials indicate the number of available bikes and cluster number. The neighborhood provided is displayed to give the user reference of the longitude and latitude entered. What did we achieve? We built a bike availability prediction model for city bike docking stations in Brooklyn. The model uses hierarchical clustering based on location and a Poisson model for bike count availability based on location, day of the week, and time of day. The Poisson model is the simplest count model with the second best RMSE and best predictor of zero availability. Also, we captured patterns of city bike use across New York City. The system-wide evaluation included all 5 boroughs and clearly denoted weekly and daily patterns based on user type. We certainly have room to grow and improve. Future work could include deploying the model as a website or smartphone app to actually get the model into users' hands. Also, the location input could come directly from the phone to make the model truly user-friendly. Next, we should continue to improve the accuracy of the zero availability predictions. A prediction of 10 instead of 8 wouldn't be a headache to a user the same way a prediction of 2 instead of 0 would be. So to improve the user experience, we should ensure zero availability is predicted accurately with higher frequency. A few more improvements include a model of all New York City, a real-time clustering to identify all docking stations within a quarter mile of the user at the time, and finally, using more availability data. 2 weeks is a short window of time, so for a larger time frame, we anticipate we could improve the model. And finally, a thank you to my graduate project advisor, Dr. Paul Bello, along with all the CUNY professors, staff, and fellow students for support and guidance throughout the Data Science Master's program.